When we're building NLP systems, the input is not words or even sentences, but rather just sequences of characters. Take this example from Pride and Prejudice. If we were to just split this by spaces, we would get this word sequence where we have 3 instances of I that differ because punctuation is still attached. So we perform tokenization, which converts a sequence of characters into a sequence of tokens. When using a standard tokenizer in this text, we get this token sequence, which has separated punctuation from words and also split the contraction I'm into I and apostrophe M. So now our 3 instances of I look the same. Most tokenizers are rule-based, manually designed by speakers of a language. But there are different tokenization conventions. One difference in English is how contractions are handled. For example, here's how 2 tokenization conventions look for a few English contractions. Neither seems perfect. Don't and aren't are maybe better handled by the Penn-Treebank convention, because the words do and are separate words. However, can't looks better under the Moses convention, and neither of them seems great for the word won't. While no tokenizer is likely to be perfect for your goals, you can tune this decision based on what works for your application. The important thing to keep in mind is to be consistent, especially if you have multiple NLP systems in use or you're using external tools or resources. You want to be sure to match their pre-processing. You can find several tokenizers in the Python nlt.tokenize library, which also has functions for splitting documents into sentences, sometimes called sentence tokenization. Tokenization gets a lot more interesting for writing systems that do not use whitespace to separate words, like Chinese, Japanese, and Thai. Here, tokenization becomes an NLP task, with manually annotated datasets and supervised machine learning. One thing to keep in mind, though, is that there are multiple conventions in use. 2 examples are shown here with glosses for each token. Different tasks may work best with different conventions, so this becomes another decision to tune for your task of interest. It's also worth noting that sometimes just segmenting into characters works well enough and definitely simplifies the tokenizer. Usually when we talk about tokenization, we're talking about adding white space. But are there cases when we would actually like to remove white space? Some examples might be for names that happen to have spaces, like New York. We may also want to do this for non-compositional compounds, like hot dog. These are phrases where the meaning of the phrase is not built from the meanings of the individual words. Though these are interesting cases to consider, in practice when we talk about tokenization, we usually just mean adding white space. Okay, now that we have a way to tokenize text, let's count the words. First, I'm going to lowercase this text. This is not something we do for every NLP task, but it is commonly done when counting words. So here are our words and their counts. There are 2 types of counts we'll be considering, for types and tokens. A word type is a unique word, that is, an entry in a vocabulary or dictionary. A word token is an instance of a type in a corpus. Given our counts from earlier, we can count the number of types and tokens in our example sentence. The type count is 21, there are 21 unique words in the sentence, and the token count is 29. There are 29 tokens separated by white space after running our tokenizer. Given the type and token counts, we can compute the type-token ratio, which is a simple but often pretty useful statistic of a corpus. So let's look at some actual type-token ratios of real-world corpora. First, let's ask this question. What do we expect to happen to the type-token ratio of a corpus as we get more data? This shows the type-token ratios for different subsets of English Wikipedia text. With more data, the type-token ratio typically gets smaller. After seeing a lot of text, you're mostly seeing words you've already seen, so the token count increases much faster than the type count. How about comparing the type-token ratio between different types of text, say Standard English and Simple English Wikipedia? Across all data sizes, Wikipedia has the higher type-token ratio. Thus, type-token ratio can serve as a very simple measure of the complexity of a corpus. Now, how about comparing Wikipedia to tweets? Well, for small datasets, Twitter has a lower type-token ratio than Wikipedia. But as we add more and more data, it actually starts to become higher. Why is this? Well, I think one reason is because Twitter shows an enormous amount of variation in word forms. For example, for the word really. These are counts computed from several million English tweets, and of course not all words show this number of word forms, but this gives you a sense of what the data looks like. How many words are there? Well, the more data you collect, the more words you find. You'll never find all the words. As we saw with these counts, the canonical form of the word is by far the most frequent one, but then there are many forms that appear only once. This reflects a broader pattern of how words are distributed in natural language. It's known as Zipf's law, and states that the frequency of a word is inversely proportional to its rank. Here in the plot, word types are arranged in decreasing order by frequency, and the y-axis shows their counts in a subset of English Wikipedia. A small number of words appear many times in a corpus, but then we have what's called the long tail, many words that appear relatively small number of times. This long tail poses challenges for data-driven methods in NLP. The majority of word types are very rare, so it's difficult to get enough data for systems to learn how to handle them. Fortunately though, even though there are many word types, we know that words have internal structure. In addition to the spelling variations we saw earlier, words have morphological structure. For example, suffixes, prefixes, compounding, and this is what we're going to be talking about next.